Alrighty, hope you guys are doing well today. What we're going to be talking about today is resistor combination techniques. So for the most part, this is going to be a review from what you guys learned in your Engineering 120 series. But we're going to go into a little bit more detail about why resistors combine the way they do, which just means we're going to talk about how Kirchhoff's laws are applied. Then I am going to spend some time working a couple of example problems that show you how I personally choose to simplify complicated resistor networks. Okay. So the first thing that we're going to look at is resistors in series. So let's say that we have the following. Where we have some resistor R1 in series with some resistor R2 in series with several more resistors until we come to some resistance, which I'm going to label R sub n, like so. And I'm going to say that this resistor network is part of some larger circuit, and the voltage drop across this portion of the network containing all of the resistors in series will be, and the current flowing into this resistor network where all of the resistors in series will be I. So the first thing that I'm going to do is I am going to label the voltage drop across each of my resistors. So I'm going to call this guy right here VR1, this guy VR2, and we'll go all the way out to VRN over here. And now I'm going to write a Kirchhoff's voltage law equation around this path. So I'm starting from the bottom left-hand corner, going across all of my resistors, and then coming back to this node. So when I write that KVL equation, what I'm going to wind up having is negative V, the total voltage drop, plus VR1 plus VR2 all the way out to that voltage VR sub n is equal to 0. And just to make our life a little bit easier, I am going to move that total voltage V over to the other side of the equal sign, which gives me V is equal to VR1 plus, excuse me, the stylus is behaving funnily, VR2 all the way out to VRN, like so. So the reason why I chose the polarity for all of those resistor voltage drops was so that that current I is flowing into the positive polarity terminal of every one of those voltages, which allows me to express all of those resistor voltage drops in terms of that current I. So the voltage drop over resistor R1 is simply I times R1. The voltage drop over resistor R2 is I times R2, and so forth until we get to the voltage drop over resistor R sub n, which is I times Rn. And we can see very easily that all of these terms have a common factor of I, so that it will look like I times R1 plus R2 all the way out to R sub n. Our equivalent resistance, REQ, comma S, so the equivalent resistance for series resistors, is, according to Ohm's law, simply the ratio of V divided by I, which comes out to be R1 plus R2 all the way out to R sub n. And for those of you that like a more simplified, a smaller form, I guess would be a way to put it, we can use summation notation and say that the equivalent resistance is the sum from I is equal to 1 to n of R sub I. Okay. So effectively, whenever we have resistors in series, we can simply add the resistor values up together. So if we had the following network that contained a 10 ohm resistor in series with a 6 ohm resistor, in series with an 8 ohm resistor, and we were trying to find the equivalent resistance looking into those terminals, we would find that REQ is just 10 ohms plus 6 ohms plus 8 ohms is 24 ohms. Once again, I anticipate that this is review for the overwhelming majority of you. Okay. So before we move along to combining resistors in parallel, does anybody have any questions about what we've just talked about?
Not yet.
All right. So let's move along then to resistors in parallel. So we're going to have a similar situation. We're going to have a network containing multiple resistors, but this time they're going to be connected in parallel. So let's this guy R2, and we're going to extend this out for n resistors in parallel. So this will be R sub n. And just like before, this may be part of a larger circuit. The voltage drop across all of these resistors connected in parallel will be V, and the current flowing into this resistor network is going to be I. So what I'm going to do now is I am going to assign a direction for all of my resistor currents. And I'm going to choose that direction to be down. So this will be IR1, this will be IR2, and this guy will be IRN, like so. So if we apply KCL at the top node and use formulation number 1, currents flowing in equal current flowing out, what we'll find is that I, our total current entering our resistor network, is simply the sum of IR1 plus IR2 all the way out to IRN. Since all of those resistors have the same voltage drop over them because they are in parallel, I can express each of those resistor currents in terms of that voltage V using Ohm's law. So that's going to look like V over R1 plus V over R2 all the way out to V over R sub n. And pretty obviously, we can see that there's a common factor of V that I can take out, leaving me I is equal to V times 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And from here, I can define my equivalent resistance, REQ, comma P for parallel, as simply, once again, the ratio of V to I. So that's going to look like that 1 over R1 plus 1 over R2 all the way out to 1 over reciprocal of that sum of reciprocals. So in a summation notation expression, that's going to look like 1 over the sum from I is equal to 1 to N of 1 over R sub I. So let's say, just for the sake of argument, that we had those same 3 resistors from our last example. 10 ohm resistor in parallel with a 6 ohm resistor in parallel with an 8 ohm resistor. And we were trying to find the equivalent resistance seen between these terminals. REQ would be 1 over 10 ohms plus 1 over 6 ohms plus 1 over 8 ohms. And I can't quite do this in my head, so I'm going to grab one of my calculators real quick. And I get 120 over 47 ohms. For those of you that like decimals, this comes out to be 2.553 and some change ohms. So those are the basics of resistor combination, okay? Whenever resistors are in series, we simply add the resistor values together. Whenever we have resistors in parallel, we add the reciprocals of the resistors together and then take the reciprocal of that sum. Now let's look at a couple of special case kind of things, all right? So what if I have a network that only contains 2 resistors in parallel? Let's call this guy R1. And this guy R2. And we're looking for REQ, right? So our equivalent resistance should be 1 over R1 plus 1 over R2. There's nothing wrong with this formulation. However, I am lazy and I know that there is a more efficient way to look at this. So what I'm going to do is I'm going to play around with some algebra here. So I'm going to multiply this term 1 over R1 by a factor of R2 over R2. And I'm going to multiply this factor of 1 over R2 times R1 over R1. And so what that gets me is 1 over R2 plus R1 divided by R1 times R2. Well, since I have 1 over a fraction, this just comes out to be the reciprocal, R1 times R2 over R1 plus R2. So this is a quick and dirty way of finding the equivalent resistance whenever we have 2 resistors in parallel, okay? But it only works for 2 resistors, okay? So to show you exactly what I mean, if we had 3 resistors in parallel, REQ would not be equal to R1 times R2 times R3 over R1 plus R2 plus R3. Can anybody tell me a pretty obvious reason as to why that doesn't work?
I mean, you're taking R1 and multiplying it by 1 over R2. So I would imagine that if you had 3, then you had to find a way to like permutate the R3 with everything else.
You were definitely right, but you're putting maybe a little more thought into this than I was expecting, actually. So if we looked at the units of the numerator, this would be ohms to the third power, and the units of the denominator would simply be ohms, which would give us units of ohm square, which definitely isn't resistance, right? So we can't do this because we won't wind up getting the right answer. Now, I want to show you guys something just really quickly here. We're going to look at that resistor network that we dealt with just a moment ago. Our 10 ohm resistor in parallel with a 6 ohm resistor in parallel with an 8 ohm resistor. And we're going to talk about how we can adapt it. Okay. So what I could do, if I were so inclined, would be to find the equivalent resistance of just these two, right? So that would be 10 times 6, which is 60, over 10 plus 6, which is 16. So 60 over 16 is the same thing as 30 over 8, which is 15 over 4. So this is the equivalent resistance of just those two that I've put the pink brace under. And now I have my 8 ohm resistor here. So my equivalent resistance is going to be 15 over 4 times 8 over 15 over 4 plus 8. So that's going to look like 30 over, let's see, 32 plus 15 is 47. Over 4, or 120 over 47 ohms, which is exactly what I got up here. So we can use that 2 resistor equivalent circuit multiple times to get our equivalent resistance in effectively bite-sized little chunks. Okay. All right, so before we start looking at bigger and uglier things, does anybody have any questions about what we've talked about here?
All good here.
All righty. So what I'm going to do is pull up your web work, and we are going to look at one of the problems and go through at least one of the iterations. So this will be homework set number 3, if I'm remembering correctly. Yeah, this is the one that I want to look at. So this problem is fairly gross. So we're going to take a stab at least one of the parts. So we have this resistor network here, which contains, if I'm not mistaken, 9 resistors connected in this ugly looking way. And we're asked to find the equivalent resistance between different sets of terminals, okay? So in part A, we're asked to find the resistance seen between terminals A and D. In part B, we're asked to find the resistance seen between terminals B and C. And finally, in part C, we're asked to see the resistance or determine the resistance between terminals C and D. So let me redraw this circuit really quickly. So this is homework number 3.2. And we have the following network. Let me look at it again really quickly. The value of the resistors doesn't particularly matter, so I'm just going to make some things up here. 100, 50, 75, 10, 80, 200. Let's make this 60, 40. And this guy right here will be 20. And go away, big thing. In the problem, if I'm not mistaken, actually, let me just look at it. All right, so this is terminal C, B, A, and D, or at least those nodes are labeled. The first thing that I would do personally is I would actually extend those terminals out, just because it helps me look at things. You're not remotely required to do this, but it doesn't change anything by giving myself a little stub of wire and extending my terminal out like so. Okay. So the first question I want to ask you guys, and this is completely and utterly arbitrary, is do you want to look at part A, part B, or part C of this problem? Any one of the three will illustrate what I want to talk about here.
Let's do C.
C, okay. So in part C, we are trying to find the resistance seen between terminals C and D, okay? So anytime I have a complicated resistor network like this, the first thing that I do is I identify all of my different nodes. And I do that using different colors, much like we did on the first day of class. So I am going to simply identify each node like so. So 4 of my nodes already have labels, so I'm going to leave them alone. And the 2 nodes that I don't have labels for, I'm going to assign them one. So I'm just going to call this guy over here E, and this guy over here F. Okay. And so what I'm going to do now is I'm effectively just going to play connect the dots with resistors. Okay. So if I'm trying to find the equivalent resistance seen between terminals C and D, what I'm going to do is I'm going to put C on one side of my page and D on the other side of my page. And I'm just going to try to figure out the different ways that I can go from C to D. I start with the simplest path first. Okay, so to me, the simplest path to go from C to D is to go through that 10 ohm resistor, because that's a straight path from C to D. So I'm just going to draw a line. I'm going to put my 10 ohm resistor here in the middle of the page. Then I'm going to make a little note here that I've already done this one. Okay. So there are multiple other ways that I can get from C to D. So I need to make sure that I include them too. The next easiest path would be to go from node C to node E and then to node D. So since I'm going through E, I'm going to put that here in the middle. To go from C to E, I go through the 100 ohm resistor. Sorry, I wrote 10 and I meant 100. Stylus isn't writing. There we go. And then to go from E to D, I need to go through the 50 ohm resistor. That takes care of this guy and this guy. Another way that I can go from C to D is to go from C to B to D. So I'm going to put node B here, also in the middle. To go from C to B, I go through the 75 ohm resistor. And to go from B to D, I go through the 20 ohm resistor. I'm going to put my little check marks. I've taken care of this guy and this guy. But there are also other paths that I can use to go from B to D, right? I could go from B to A to D, which means I'm going to put A right here. I can go from B to A using the 80 ohm resistor. And then I can go from A to D directly through the 40 ohm resistor. And then there's also that path where I go from A to D through node F. So I'm going to put F right here. And so to go from A to F is through the 200. And then from F to D is through the 60. And if I am not mistaken, I believe I have accounted for every different path that I could take to get from C to D. So what I'm going to do now is I'm going to relabel these nodes. I'm not going to go into as much detail. This guy right here in red is C. This guy over here on the right is D. So I'm just reusing the same colors. So that's going to be blue. Let's see while I'm at it. F is in purple. A was in orange. B was in green. And E was in pink. So now I'm going to start combining resistors together. Generally speaking, I'm just going to work from the bottom and then work my way towards the top. So how are the 200 ohm resistor and the 60 ohm resistor connected to each other?
In series.
Yes, they're in series. So I'm going to replace that 200 ohm resistor and that 60 ohm resistor by a single equivalent resistance that will be 260 ohms. So because I'm placing this resistor between, or I'm replacing a path that goes from A to D, that equivalent resistance is going to show up between A and D. So I'll just have one resistor here. And 200 plus 60 is 260, right? So now, how are the 40 ohm resistor and the 60 ohm resistor connected? Or excuse me, the 40 ohm resistor and the 260 ohm resistor.
Those are in parallel.
Exactly right. So I'm going to replace that. So I'm going to have 40 times 260 over 40 plus 260. My calculator tells me that that is 104 over 3. So because both of these resistors are between the yellow node and the blue node, I'm going to replace it with a single resistor between, or excuse me, that orange node and the blue node. So 104 over 3 ohms. How are the 80 ohm resistor and that 1/4 over 3 ohms connected?
Series.
They're in series, so I'm just going to add 80. So that gives me 344 over 3. And I'm just going to keep going, right? So now I can see that the 20 and that 344 over 3 are in parallel. So in my calculator, that's going to be answer times 20 divided by answer plus 20, which I get to be 1,720 over 101. That is in series with 75. So I'm going to combine these two together. Which would give me 9295 over 101. And there's nothing more that I can do to simplify that bit there. So now I'm going to move to the next path above it. So it looks to me like 100 is in series with 50. So I'm going to replace that with a single 150 ohm resistor. And now I just have 3 resistances in parallel. So I'm just going to have 1 over 1 over 10 plus 1 over 150. And then I'm going to have 101 over 9295. And if I did this right, I get 8.508 and some change ohms as the equivalent resistance seen between, let me rewrite this, C and D. So this is just the way that I choose to simplify complex resistor networks. And it is literally just playing connect the dots with resistors and keeping track of which different paths that I've taken. Do you guys feel comfortable with this, or would you like me to work another example?
No, I understand it.
Okay.
I guess I'll ask, I mean, is there anything like tricky to look out for with these that you suggest?
No, if you're methodical about it, which I tend to be, then it'll all work out okay. The only thing that I can really tell you is to not get lazy with it. It's easy to make simple mistakes if you're not paying attention. So just pay a lot of attention. I know that sounds a little flippant, but it's true. Let's take a look at some of the other web work problems here just to see if there's any questions. Right. So this guy here is very similar to our last problem. The network isn't quite as complicated, but instead of resistances, you're given conductances. So what I would encourage you all to do is to just take the reciprocal of those values. So for instance, the conductance G1 is 38 millisiemens. So the resistance would be 1 divided by 0.038 or 26.316 ohms. Once you convert all of those conductances into resistances, you can use simple resistance combination techniques like we've been doing, okay? So nothing real wild or crazy there. Just convert all of those conductances into resistances, and then you can directly apply everything that we've done. For this problem, we're just looking for, well, this is kind of illustrating how you can use equivalent resistances to make your life a little bit easier. So let me work part A and part B of this problem to kind of show you what it's intending for you to do, okay? So let's see, so we have a source voltage. Let's see, this is homework number 3, problem 4, if I'm not mistaken. We have some voltage source here. I believe it's 80 volts. Here we have a 100 ohm resistor. And then a 50 ohm resistor over which you're trying to find the voltage drop. V1. Let's see, R1 is 20. And then we have this guy right here, which I believe was said to be 140. This is the voltage V2. Then we have R3, which is 75. This resistor here, which is 180. If I'm not mistaken, we're also asked to solve for this current I, like so. And things are kicked off by having a dashed line. And you're asked in part A to find the equivalent resistance of everything to the right of this dashed line, right? So what we could do is we could literally disconnect that portion of the network and find the equivalent resistance. So that would look like 20, 140, 75, and I wrote down 180, but in my problem, I think it says it's 480, so let me correct that really quickly. Yeah, 480. So what would this look like? This network is simple enough to where I don't expect you to be able to look at it and give me a numerical answer, but I do expect you to be able to look at it and figure out what you need to do pretty quickly.
Would we, I would combine the two in the top first, so 75 and 20, and then with the 48, and then I would solve with the parallel equation for 140 and the sum of the 3 values.
So you've made a little bit of a mistake there, okay?
Okay.
The 20 and the 75 are not in series, nor are they in parallel, so there's no way to combine them. So when I look at this thing, and I'm about to introduce a notation that I'm going to use throughout this class, what I would see would be 20 ohms in series. So I'm just going to put plus the combination of 140 ohms in parallel with the series combination of 75 and 480. So the 75 and 480 are in series because there is one point of interconnection between them with no branching paths. So that's an obvious series connection. And then once I combine those two into a single equivalent resistance, that single equivalent resistance, which will be 455, will be in parallel with that 140. And then that equivalent resistance of all of this stuff is just in series with the 20. Is that clear?
Yes, thank you.
Yeah, no problem. So throwing this in my calculator really quickly, I would have 20 plus, and I'm going to use the fraction button, 140 times 75 plus 480 over 140 plus 75 plus 480. And I get 18,320 over 139, which I'm just going to leave it like that because I have a calculator. Okay. So from here, I could redraw my original circuit. Sorry, this was an 80-volt source. All right. The ohm symbol should be there. And this is the voltage V1, right? Well, how could I solve for the voltage V1 now? Well, these two resistors, the 50 ohm resistor and that 18,320 over 139, are in parallel, which means they have to have the same voltage drop over them. So from here, I could combine those two resistors together, leaving me with 80 volts in series with 100. Series with, let's see, 50 ohms. $36.2485 and some change ohms, over which we're trying to find the voltage V1. So I could say that this current I would be 80 volts divided by 100 ohms plus 36.2485 ohms. Which comes out to be 0.5872 amps. And from here, V1 is just that 0.5872 amps times that 36.2485 ohm resistance. Or 21.2838 volts. So I've used nothing but resistor combination techniques to get this circuit down until it looked like a single loop circuit. Then I used Ohm's law to find the current flowing around the single loop circuit, and then used Ohm's law once again to find the voltage drop over the specific equivalent resistance that we were looking for. And from here, once you know V1, you can do a similar thing to figure out, what portion of V1 is going to show up at V2. And then once you know what V2 is, V2 divided by 75 plus 480 gives you the I that you're looking for. Okay. In our next class meeting, we are actually going to learn about voltage division and current division, which will give you a little bit easier way to work problems like this, where you have multiple voltages that you're trying to find in a weird configuration, but we'll talk about that more on Monday. All right, so we've talked about resistor combination techniques. We've applied it a couple of different times. Does anybody have any questions?
On homework, see problem 3, that switch, I assume we kind of just treat it as if there's not a wire there.
So let's talk about it really quickly.
Okay.
Great question. So in part A, you're asked what the resistance is if the switch is acting like an open circuit. So you're 100% right. When the switch is open, treat it as if there is literally nothing there. In part B, the switch is replaced by a short circuit, which is just a wire. Okay. I may not have actually talked about that explicitly, so let's talk about the concept of open circuits and short circuits here really quickly. I should have talked about it on Tuesday, but it's very likely that I forgot. So on the left-hand side here, I'm going to represent an open circuit. And on the right-hand side here, I'm going to represent a short circuit. Okay. So for an open circuit, we are just going to have literally 2 open terminals with nothing connected to them as part of a larger circuit. Okay. So how much current, let me write here, is able to flow through an open circuit? Take a wild guess.
None.
None. You're absolutely right. No current is allowed to flow through an open circuit in this class. I say that specifically because, as many of you have probably observed at some point in your life, whenever you unplug things from the wall, sometimes you will see sparks. Those sparks that you're seeing is current trying to flow through the open circuit that you just created by unplugging things. And effectively, Lenz's law and Faraday's law of electromagnetic induction are providing a large enough voltage to ionize or kind of create a plasma to keep that current flowing for as long as you can. In our class, though, anytime we have an open circuit, we are going to assume no current can flow through it. So since no current can flow through it, what should the resistance of an open circuit be?
Would it be like infinite, or well, no? If it's possible.
No, you're exactly right.
Okay.
For an open circuit, it appears as if it's an infinitely large resistance. 100% correct.
Okay.
On the other side of things, we have short circuits, which we're going to represent as literally just a wire. Okay. So what should the voltage drop across a short circuit be?
None. There is no drop.
Exactly right. So the voltage drop across any short circuit that we see, sorry, my screen keeps scrolling on me, will be 0 volts, because in this class, we treat wires as if it's effectively, we treat wires as if they have no resistance. And from Ohm's law, any current times a resistance of 0 is going to give us a voltage of 0 volts, right? So anytime you're asked anything about a short circuit, these are the parameters that you're expected to use. Anytime, excuse me, an open circuit, anytime you're asked anything about a short circuit, these are the parameters that you're expected.
That's great. Thank you.
Yep, no problem. And sorry, I forgot to mention that in class on Tuesday. Speaking about things mentioned in class on Tuesday, just really quickly here before I wrap things up. If you go to the exam 1 section on Moodle, you should now see the little practice thing that will get you to download Respondus and all that kind of stuff. I actually need to make sure that I set it up correctly. So let me check that really quick.
We do get limited attempts on this practice test, right?
Let me play with the configuration here and make sure that I'm not talking out of my ass. So if we go to exam 1, here it is. So you want unlimited attempts to play around with it. I believe I can set that up. Restrictions on attempts. I don't think there are any here. Let me look through. Timing is set correctly. Oh, set for 3 attempts allowed. Let's just put it as unlimited, but it shouldn't matter. All right, and then just while I'm at it, go to the lockdown browser dashboard. If the link will go. All right, yes, so it says it is required. Require the lockdown browser for this exam, require automated proctoring. So it's going to run that startup sequence check. It's going to make sure that it can see your face and then notify you during the exam if it can't see your face and all of that kind of stuff. Let me see if there's any other advanced settings that are weird here. No. I'm effectively already having you guys do this show your work thing by submitting your work to me digitally, so I'm not going to enable that yet. So it should be configured correctly that it'll make you download Respondus, go through all of the exact same steps that you're going to be asked to go through when you take one of your real exams and all that kind of good stuff.
So this might be a kind of a annoying question. This is my testing environment, and I've got a big iMac here. So like my work environment, like that's as far down as I can go. Should I just try to practice testing on my laptop maybe?
Let me,
or do you,
I don't see you, so let me see you.
Oh.
Yeah, sorry, I have
no, it's okay.
everybody's things minimized, but I just opened it up. So I mean, it looks to me like you're in a living room.
It's our garage.
Yeah.
And then try to I don't want the lap to get
I
disconnected.
also have a massive computer as well.
I know that's annoying. That's got to be annoying. I don't know. I mean, I could practice on my. I could get used to it on my homework on my laptop.
Whatever
What do you
makes
think?
you the most comfortable, I think, like in my opinion, you don't want to add too many extra stressors and all of that kind of
Right.
stuff when you're trying to take your test. So I mean, if you're just using, your regular workspace and all that kind of stuff, and you've got a little space off to the side that you can do work on, that's fine. Mainly what I'm interested in is kind of being able to see that you're not playing on your phone and stuff like that.
Okay.
I mean, if it looks like you're earnestly trying to work on the exam, then I'm okay.
Cool. Okay. Thank you.
Are there any other questions about anything?
None here.
All right. Well, I hope you guys have a great rest of your afternoon. I am going to go back to orientation and start helping those freshmen out again. If you need anything, you can shoot me an email or send me a text. My cell phone number is on the syllabus. All right. Thank you, guys. See you on Monday.
Thank you. You have a good day, Dr. Hartman.
You too.